Here we are at the final stage of developing our mechanical analog in electrical form. Notice now that we have added some components to the system, one being the motor. This motor is connected to the shaft of the differential variable capacitor. And its purpose is to rotate that shaft for us, left and right. And this motor is connected to a motor speed control circuit. And the purpose of the motor speed control circuit is to control the rate at which the differential variable capacitor shaft is rotated. So if the motor is attached to the differential variable capacitor, we call it DVC, that turns at the same rate in both directions, then we can calculate the mass flow rate that we were simulating as the capacitance range of the differential variable capacitor divided by its full rotation time. This rotation time can be seen in the waveform as the area between the dotted line. This is the time where the capacitance is sloping up or down. That is the full rotation time. We can use this motor speed control to set this rate at a desired value. So the complete circuit is shown here with an ammeter and current source combination represented by the symbol between the M1 and M2 capacitor blocks. Each block has its own independent voltmeter to measure the analog of velocity. Going through the waveforms, we can see how the simulation should proceed. We'll start, say, with the capacitor C4 at its maximum value. And while that state exists, we turn on the current source, the positive current, and that simulates a force pushing these two masses apart. That current stays on for its desired time, and at the end of that time, the motor rotates the shaft of the differential variable capacitor, so that now, as the capacitance C4 goes to 0, the capacitance C3 goes to the maximum capacitance value at the same rate. After this motor speed control rotation of the motor is complete, we now reverse the polarity of the current source, and this is the equivalent to a force trying to pull the two masses together. We let that go on for our desired amount of time, and the voltmeter measures the voltage waveforms that result. The ammeter measures the current waveforms, and from these waveforms we equivalently divine our voltage and velocity events in the mechanical circuit. Then we repeat that sequence, going back by rotating the shaft in the opposite direction so that C3 goes to 0 at the same rate as C4 goes to the maximum capacitance again. And once that rotation is complete, we turn on the current. This time in the positive direction, again simulating pushing the masses apart. And the ammeter and voltmeter captures those waveforms. Rotating the shaft now to reverse the mass flow back to C3 and off of C4. Current turns on in the opposite polarity, simulating pulling the masses apart, and so on. We continue this sequence until we have a certain amount of waveforms, maybe 4 or 5, from which we can find out the behavior of the mechanical system through the behavior of the electrical system. Notice that the waveform shows that we have a 120-degree difference between when the capacitance starts to rotate the shaft so every 120 degrees we get a rotation of the motor speed control. That is the phasing of this simulation sequence. So now looking at this, you have the basic information that you need to build an analog computer to simulate the mechanical system. In the actual implementation, you may discover that you may have to put in some resistances and other components for safety's sake to protect your ammeter, voltmeter, and circuit components. As long as you do the same thing to both blocks of the circuit and mathematically take into account what the effects of these additional elements that you might add may be, then you will be okay with this. Good luck, and thank you for attending this lesson.